So next we're going to do the same thing for magnesium hydroxide, which has a similar KSP expression of KSP equals concentration of Mg2 plus times the concentration of OH minus squared. Don't know the concentration of OH minus, but we do know the concentration of Mg and the KSP value. So we have 6.3 times 10 to the negative 10 divided by 0.35 molar. And then remember, we have to take the square root because we have OH minus squared. So that means our concentration of OH minus for precipitate to form has to be 4.24 times 10 to the negative 5 molar. So then I'm comparing these two values. Which one is smaller? The one for MgOH, magnesium hydroxide, is smaller. So magnesium hydroxide will precipitate out first because this concentration of OH minus will be reached before the other concentration of OH minus. For number 15, the question asks, explain why the solubility of AgBr decreases when sodium bromide is added to the system. So the equation for the dissociation of silver bromide is AgBr. Silver is typically a +1 ion. I don't know if we went over that or not. I know it's transition. Particularly, it's just a +1 ion. So it's just AgBr yields Ag plus 1 plus Br minus 1. So when NaBr is added to solution, sodium bromide has sodium in it, so NaBr dissociates 100% because it is completely soluble in water into sodium ions, Na+, and bromine ions, Br-. Now we're not really worried about the bromine or the sodium ions, we're really just worried about the bromine minus ions. So when this happens, when we add sodium bromide, the concentration of Br- increases. This increase in concentration causes a stress on this equilibrium. So if we increase the concentration of Br-, that shouldn't be plus, that should be minus. If we increase this concentration, it will shift equilibrium to the left. On the left side, we have this solid silver bromide. So it lowers the solubility of silver bromide because it pushes it to the left towards the solid where a precipitate will form rather than ions forming in the solution. For number 16, the solubility product constant for silver sulfate is 1.2 times 10 to the negative 5 at 25 Celsius. We want to find the concentration of silver and sulfate after 0.755 grams of silver nitrate are added to a 500 milliliter saturated solution of silver sulfate and equilibrium is established. Assume the total volume remains the same and the final temperature is 25 degrees Celsius. So basically we are adding silver ions to the system, and due to that common ion effect, we're going to affect the equilibrium concentrations for these two substances. So first I'm going to just kind of write out the equation just so I know what's happening. So you have Ag2SO4 dissociating into 2Ag plus SO4 2 minus. Okay, our KSP is equal to 1.2 times 10 to the negative 5 at 25 degrees Celsius. We know that the KSP, 1.2 times 10 to the negative 5, is going to be equal to the concentration of Ag squared times the concentration of SO4. So I'm going to write that, since sodium is a 2-to-1 ratio for formula units, I'm going to write 2S squared times concentration of S, which equals 4S cubed. And S is equal to 1.44 times 10 to the negative 2 molar. Okay, so at this equilibrium, the concentration of sulfate is 1.4 times 10 to the negative 2. I'm going to say equals sulfate. And then the concentration of silver is going to be 2.8 times 10 to the negative 2 molar. Now we are adding silver to the solution, so that concentration is going to change. Okay, I'll let you look at that for a little bit. So we're going to take this concentration of silver, 2.88 times 10 to the negative 2 moles per liter. I'm going to multiply it by the volume of solution, which is 500 milliliters. And I know that I have 0.0144 moles of silver. From those grams that I add, so I have 0.755 grams of silver nitrate. I'm going to find how many moles that is. So 1 mole divided by the molar mass, which is 169.88 grams. Now that's moles of salt. I'm only interested in moles of silver. There is 1 mole of silver for every 1 mole of silver nitrate. So it is a 1-to-1 mole ratio. So I find that this sample adds to my solution 0.0044 moles of silver. Now I'm going to add these 2 moles of silver together. So I have 0.0044 plus 0.0144 moles divided by the total volume of the solution, which they say stays the same. So that's 0.5 liters. And that gives me a concentration of silver ions to be 3.7 times 10 to the negative 2 molar. So that is my new concentration of silver. Okay, now I'm going to kind of go back here. So it did increase from 2.8 times 10 to the negative 2 to 3.7, which is what you expect when you add silver to the solution. Our KSP value is a constant. That's what K means. So our KSP value is going to remain at the same temperature, 1.2 times 10 to the negative 5. Okay, we increased the concentration of silver, so that's going to be 3.7 times 10 to the negative 2, and we have to square it, again because of that coefficient, and now you want to solve for the new concentration of SO4. Okay, so if we divide 1.2 times 10 to the negative 5 by 3.7 times 10 to the negative 2 squared, we get the concentration of sulfate to be 8.8 times 10 to the negative 3 molar. And depending on sig figs, you may get something closer to 9. So if you rounded down here, I carried a lot of decimals. If you rounded anywhere down here, you might get something closer to 9.3 times 10 to the negative 3 from rounding. So you might get something like 9 point something here, but that's just due to rounding. Okay, so that is the end of the worksheet. Let me know if you have any questions. I can always meet with you to answer those questions or make another video, whatever you prefer. Okay, have a wonderful day.